All right, so here's a second example of induction, and this one is involving divisibility. So again, we're not going to do the formal proof here, but we're going to kind of walk through the quote-unquote scratch work to kind of figure out the base case and the inductive case and what's going on here. All right, so here's what we're trying to prove, that 7 to the power n minus 1 is a multiple of 6 for all natural numbers n. Okay, so the first thing that we want to do is our base case. Come on, there we go. All right, so in this case, since we're doing all natural numbers n, that's starting with n equals 0. So we're gonna plug in n equals 0 to this, right? So it's 7 to the power 0 minus 1. Or of course, any number to the power 0 is 1. So this gives us 1 minus 1 is 0. And it turns out that 0 is a multiple of 6. And that's because 0 is equal to 6 times 0, right? So it is, in fact, a multiple of 6, even though it doesn't really almost feel like it. If we wanted to check, and again, this isn't part of the base case, but if you want to just kind of make sure that you actually believe this, you could plug in maybe n equals 1 and n equals 2. So if you get n equals 1, then you get 7 minus 1 is 6, which is, of course, a multiple of 6. 7 squared is 49, minus 1 is 48, which is 6 times 8. All right, and again, you can check a few more if you're not quite sure that you believe it yet. All we need for the base case is just the n equals 0. These other examples are just to kind of make sure that we're on board. All right, so next we move on to the inductive case. All right, so for the inductive case, we get to assume that the statement is true when n equals k. All right, so I guess I kind of forgot to do our statement up here. Would be p of n is that 7 to the power n minus 1 is a multiple of 6. Or in other words, is divisible by 6. All right, so we get to assume that p of k is true for our inductive case, and then we want to show that p of k plus 1 is also true. All right, so when we assume that p of k is true, what does that mean? That means we get to assume, that 7 to the power k minus 1 is a multiple of 6. All right, so again, basically all we're doing is changing our statement p of n. We're changing the n into a k. All right, so that's why we get 7 to the power k minus 1. All right, so what does it mean that that's a multiple of 6? Well, that means there exists an integer. We can call it L. All right, so there exists an integer L such that 7 to the power k minus 1 is equal to 6 times L, right? Because that's what it means to be divisible by 6 or to be a multiple of 6. All right, now where can we go from here? What we want to show is that p of k plus 1 is true. Well, what is p of k plus 1? That would be 7 to the power k plus 1 minus 1 is a multiple of 6. All right, so the question right now is, how do we get from here, 7 to the power k minus 1, to 7 to the power k plus 1 minus 1? Well, the way that we're going to do that is take this equation right here, and we're going to multiply each side by 7. Okay, and of course we know that that's a perfectly valid mathematical thing to do, to multiply an equation by 7 on each side. So we have 7 times 7 to the power k minus 1, and that'll be equal to 7 times 6 to the L. All right, so you can see I haven't done anything. I've just taken this equation and multiplied it by 7 on each side. That didn't change the equality. All right. But keep in mind here, so what we want to do is now distribute this 7. So we have to distribute it to the 7 to the k and to the 1. All right, keep in mind that that's really 7 to the first power. And since we're multiplying, we add, since it's the same base, we add the exponents. So that gives us 7 to the power 1 plus k, or 7 to the power k plus 1, and then minus 7. So take a minute to make sure you remember those exponent rules and why that's working the way it does. And then on the right-hand side, 7 times 6 is, of course, 42L. All right, so what we have here, what we just wrote down, is close to what we're looking for over here, right? What we're trying to show is 7 to the power k minus 1 is a multiple of 6. But here we have minus 7, all right? Well, how can we make that look like 7 to the power k minus 1? Well, what if we just add 6 to each side? Then we would have 7 to the power k plus 1 minus 7 plus 6 is equal to 42L plus 6. Okay, so again, take a minute to believe, to make sure you believe that what I just did was valid by adding 6 to each side of the equation. That doesn't change anything. But now when we simplify this left-hand side, we have minus 7, and then plus 1 would be minus 1. And then what can we do to the right-hand side? 42L plus 6. Well, both of those terms have a common factor of 6, so we could factor a 6 out, and then we'd be left with 7L plus 1. Okay, make sure you're careful with your factoring here. And then, of course, nothing changed on the left-hand side. All right, what do we know about this right here? 7L plus 1. This is an integer. Okay, therefore, we've just shown that 7 to the power k plus 1 minus 1 is a multiple of 6, or saying the same thing, it's divisible by 6. All right, and that's exactly what we wanted to show. We were trying to show that 7 to the power k plus 1 is a multiple of 6. All right, so that's kind of the scratch work of the calculation, and then below this you'll see the